Good afternoon. My name is Joan Johnson Fries, and it is my pleasure to chair this fifth panel on institutional arrangements in solar system exploration. We have four papers to be presented by four astute individuals who will consider relevant issues based on their experience and their research. All their bios are available to you, so I won't take the time to go through them. I will just briefly mention, we have Jim Burke from JPL, the legendary Jim Burke. It's been my pleasure to work with him for years with the International Space University. John Sarkosian, an operations scientist at CSIRO, which I looked up, and it's Commonwealth Scientific and Industrial Research Organization from Australia. Michael Neufeld, museum curator in the Space History Division at the National Air and Space Museum, and Peter Markovsky, a PhD candidate in History of Science at the University of Oklahoma. The issues they will be considering are several. Institutional management, for example, will be considered, as will institutional focus. How management issues, arrangements, and focus can affect the ability to execute a highly sophisticated science and engineering program. And we've already been hearing about that this morning through different international collaboration examples. And these papers will consider and go into depth on those issues, including international collaboration, the complexity and the potential that is added by expanding missions beyond national, or extending missions beyond national borders. And clearly the complexity expansion is across the board, not just with the science and engineering considerations, but with the political and legal. One point that has really fascinated me over the years as an observer and analyst of these institutional arrangements is the role, and perhaps changing role, of the program manager. I'll give fair warning now to the panelists that that'll be a question I will be raising to them, and I hope you, the audience, will be noting your questions that they can address as well. We'll follow the same format as we have already, 20-minute presentations, 5 minutes of Q&A, and then the panel will assemble at the end. So with that, I would like to introduce Jim Burke to talk about the foundations of solar system exploration at JPL, how the first mariners and rangers built them.
Thank you, Joan. I'd like to begin by giving you a little background on the co-author and my successor as Ranger Project Manager, Bud Schirmeyer. Many of you, of course, know him from his distinguished later reputation at JPL as project manager of various projects, Mariner 6 and 7, and the Voyagers, as of when they were launched. He was one of the first of a long succession of excellent project managers on Voyager. But what I'd like to do here is take a couple minutes to tell you a little bit about the earlier part of his life. He and I graduated from Caltech after meeting each other as freshmen 70 years ago. 70. And while we were at Caltech, we, of course, enjoyed all the Southern California recreations: soaring, sailing, skiing, surfing, whatever else there is that doesn't begin with S. He brought me down off the mountain with a broken leg twice. So we know each other pretty well. And in any case, it was my very good fortune to have him in position as manager of JPL Systems Division, which is where all the subsystems get to try to work with each other. That's what he was doing while I was being the first project manager of Ranger. But our experience at JPL went way back from there. We both were hired in 1949. So that by the time Ranger came along, we both had been working at JPL for more than 10 years. And one part of what I'm going to tell you from here on is how there was a collision between us and everybody else involved in the project, all the way up to Congress later in the game. Because we really thought we knew what we were doing. We were experienced, both of us were experienced project managers under the Army, and we knew how to do what we were doing. Ranger presented us with a more complicated and bigger project to do, but not one that was different in any essential way from the things we'd been doing before. Therefore, there was a definite collision between us and our leaders once we were transferred out of the Army and into NASA. Because NASA had a whole lot of engineers who were just as experienced and just as smart as us, and it took us a while to realize that they were our bosses. So that's a little bit the theme of this presentation, okay? Oh, I don't have a script. Well, no, I can't read it up there. I'll have to read it here. Sorry about that. JPL, of course, launched the first Earth satellites, Explorer 1, 4, 5. But quickly it was determined that Earth satellites were going to be a big business in a crowded field, and we as a university laboratory shouldn't really be in that field. So we chose to go beyond low Earth orbit, first target being Mars for the 1960 the 1960 launch window, which was the first time in human history that something could be launched to Mars. So that was the objective initially. Retreated back from that, driven by circumstances, to the moon. That was the process as of 1958. Okay, the von Braun team, very experienced, of course. We had to go through quite a transition with them because they ended up in a very anomalous position. Once NASA was formed, the von Braun people were NASA's agent for procuring launch services from the Air Force. If you can find a more difficult situation for somebody, that's where they were. And it's to their great credit that individuals in both the Air Force and the Army saw to it that in spite of all the institutional rivalries and other things that were happening at the time, they managed to pull it off. They got us our launch vehicles. Tremendous confusion, not just about launch vehicles, but really about everything as to who was going to do what. But rather quickly, in 1958 and 59, we discovered that we just couldn't do that Mars launch window. It was way beyond anything we could logically hope to meet. So the big Mariner, called Mariner A, that was planned for that mission, was abandoned, and was decided to build a Mariner for Venus in 1962, a couple of them, that would be derived from the smaller Ranger lunar spacecraft that we were building. Ranger already had solar panels and a high gain antenna, because those are features that you have to have for interplanetary missions. You don't need them for the moon. But we had them on Ranger because we visualized it as a precursor to planetary missions. 3-axis attitude control, pointing an antenna, getting solar power, and being able to execute a mid-course maneuver, trajectory correction. Those were the features that had to be on the Mariner, so they were on the Ranger. And the Mariner became to be called Mariner R, derived from Ranger, okay? Mariner A became Mariner R. Okay, the Air Force and our Huntsville friends got us the Atlas Agena, the Deep Space Net and Space Flight Operations Facility, necessary for both lunar and planetary missions, began building at that time. Common bus variable payloads. everything you see on this slide was an attempt by us to try to meet the requirement of building reliability through successive operations and still meeting the difficult demands of planetary missions where you can't change the schedule unless you're prepared to slip it for years, as in fact did happen with Curiosity, the big rover. Okay. Science on every flight. I had what now seems a very peculiar attitude about science. I insisted that every flight carry scientific instruments for two reasons. One, we didn't know which flight or flights might succeed. Two, engineering development of science instruments in flight is as important as that of any other subsystem on the spacecraft. And I simply thought it's up to the project manager to figure out, after receiving advice from scientists and comparing that with what you can do, what you can accommodate, then I'll tell the scientists which of them get to come and which other ones have to wait for another launch. Can you imagine a viewpoint more different from that of, first, science is the objective of the mission? Come on, guys. Two, there's a whole structure out there of scientific advisory committees, NASA and this and that. Project manager simply has to sit and watch all of that happen and then deal with the result. Well, that wasn't the way I started. October 1960, I was appointed project manager. On the 10th of October, big rocket takes off. It was the classic old original one, except the upper stages weighed more than 30 tons. And we watched the very slow acceleration of that and thought, oh my goodness, what is this thing? Then on the second one, on the 14th of October, our telemetry was good enough to show that it had four big boosters going off like that. So that was when we first began to understand what the Molniya configuration of the Soviet launch vehicle looked like. When President Kennedy was inaugurated, he gave a talk that was very largely about the contest between American values and the subversive and threatening emanations that were coming out of the USSR. On the 4th and 12th of February, as you heard this morning, they got two launches off, and the second one sent Venera 1 on its way. Then Yuri Gagarin, Kennedy announced Apollo. If you can imagine a more propulsive environment than the one we were in to get Ranger 1 and 2 going, we had a lot of pressure on us. Much of it provided by ourselves, and we really wanted to get going, and we did. Things moved fast. I skipped over a whole lot of trouble. Originally, when NASA when we and the Germans were transferred into NASA, we already had a plan for upper stages on the Atlas, but they were not the right ones. The Air Force Agena was the right upper stage to use, but it took, oops, how did that happen? I'll go back. I went back too far, sorry, okay. Huh. What happened? Okay, never mind. Something about the launch vehicles was on the slide that is now missing. Oh, okay, all right. Marshall was placed in a very tough position, but we did end up, again because of the dedication of individuals in the agencies who put our needs above the interagency disputes that were all going on then. We got the launch vehicles that we needed. I told you about how we didn't really like being jerked around by people who were our essential colleagues professionally and suddenly turned out to be from NASA, a new agency that we'd never heard of, and they were in charge. Our lunar scientists were the leaders in the profession. Geochemistry, gamma ray spectrometer, geophysics, seismometer, and geomorphology, the television. Those were the instruments on the Lunar Rangers, and the scientists in charge of those did not give us any trouble. They really did a tremendous job, and they are famous for it. They were already famous in their own professions, of course. We had a problem with non-lunar scientists, space physics, and I'll get to that a little later. Okay, and we had a sort of a philosophical problem with not the lunar scientists. They were fine, they were on board, they followed our schedule. Ranger 1 and 2 were planned as test flights, not aimed at the moon, but to have a high enough apogee that they would take the spacecraft out to where it could acquire the sun and earth references. And since it was going to do that out in the magnetosphere, it might as well have some space physics instruments on board. It had an excellent payload designed by the prominent space physicists of the day, plus an ultraviolet telescope looking back at the Earth's hydrogen corona. 3, 4, and 5, I told you about their instruments, and on Ranger 6 to 9, the objective was reduced to just television. Now, here's the example of the bus with one of the several different payloads. The bus is hexagonal because of a vanished upper stage configuration, so it was adapted to the Agena. The tower on the top has the space physics instruments, and at the very top, the omnidirectional antenna. So that was the configuration of Rangers 1 and 2. Ranger 1 and 2, because of Agena upper stage troubles, never got to their high apogee orbits. They were stranded in low Earth orbit. The spacecraft appeared to be okay as far as you could tell in that orbit. Ranger 3, we had a spacecraft that was fine. It was injected. The Atlas had a guidance error, but the Ranger acquired the sun and earth and began to do what it should do. But then when the mid-course maneuver happened, one vector was pointed the wrong way. There had been a double sign inversion between the spacecraft and the ground equipment, so it missed the moon. Ranger 4, something got across a couple of pins between the Agena. When the spacecraft came away from the Agena, something shorted out the Ranger. If it had had the female side of the separation connector, that probably wouldn't have happened. On Ranger 5, I'll show you a picture of that one. But Ranger 6, this is after I had been replaced as project manager by Bud Schermeyer, and I'll tell you more about that later, but here's this brief version of the story. When the Atlas staged its first stage engines off, a plasma cloud enveloped the vehicle and shorted out the television. Fascinating. This is the configuration of the lunar ones with the seismometer ball at the top and the gamma ray spectrometer out on a boom and the television looking down. I seem to keep skipping over slides. Well, okay. This is the power switching and logic unit in Ranger 5, proof test model of it. Shows you something about our packaging. People look at JPL's packaging and they say, hey, those look like locomotive parts. Well, we found out they have to look like locomotive parts if you don't want to amplify vibrations from the launch vehicle, etc. and that's why our packages look the way they do. A backside of this little item, you see the arrow pointing there, that screw got warm and that did us in. We had a good spacecraft. Again, it had acquired the sun and earth, was on its way to the moon this time. Atlas Agena was okay, fine. But then we went to the Ranger 6, 7, 8, and 9 configuration with just television and a crash into the moon. Okay, that's what I'm here to tell you. Robotic deep space exploration demands extreme attention to risk, and even then, you don't always succeed. Technical risks, all the ones in the Ranger, both in the launch vehicles and the spacecraft. The failures were at interfaces. Management risks, I guess I don't need to go too much into that. But after Ranger 5, the project capsized and Schirmeyer replaced me. Then he had the failure of Ranger 6, which took it all the way up to Congress. Enormous trouble. And everything was focused on the RCA camera payload, while in fact, the failure happened during the Atlas booster staging back during ascent. So, big, long failure investigation entirely focused on the place where the failure didn't occur. And we may never have known about the cause of that failure had not a solar physicist among us continued to persist in looking into it and investigating all the records, and he finally decided he had a convincing story, and he took it, not to the project manager, but to his division manager, who thought about it and said, that's interesting. But it was quite a while before everybody became convinced that that was the actual cause of the failure. When a plasma cloud went up the sides of the Atlas and back down, for just less than a second, it was enough to turn on the TVs and burn them out. Thank you. I put a couple of my references in here. I sort of stretched the point a little bit. Thank you, Joan.
Right on time, so go ahead and take 5 minutes. No, go ahead and take questions.
Okay. Yeah, okay, since I'm going to ask myself one question, why did you put this in about yes, reference 4, 1966, declassified 94. The beautiful book by Wes Huntress and Mikhail Marov tells the real story about all of the Soviet missions. What this reference is my story about what we thought they were doing, published in the Studies in Intelligence, and wasn't declassified for a number of years.
During your days at JPL, I was at ABMA. I was with the Army Ballistic Missile Agency back in those 50s years, and you guys were transferred in October '58. We held out with the Army until July 1960. The Army didn't want to lose the von Braun team, and it was finally Eisenhower who personally intervened, and so we transferred officially on the 1st of July 1960. Also, we developed the Jupiter IRBM. But then you got the Air Force. We were told that the Army was not going to deploy that missile, that it was going to be deployed by the Air Force. So we had to paint out U.S. Army, put U.S. Air Force in there, Redstone Arsenal filled with Air Force personnel, learning how to operate the Jupiter IRBM, which was deployed in Turkey. But that Jupiter put in your upper stages. You remember the Juno 2?
Oh, yes, of course.
You didn't talk about that. Could you say a few words about Juno 2?
I said the launch vehicle picture was a little bit confused. That was a strong understatement, and you've just heard a little more about some of the various pieces of spaghetti that were all squirming around there. Go ahead.
Jim, can you just talk a little bit about how you and everybody realized the seriousness of the reliability issues? What did you expect going in? Did you think you could just get away with, seeing if it worked, and if it didn't work, you'd fix it? But then, was there a moment when you all realized that you were in a much more unforgiving game?
I think the answer, the best simple, quick answer, short answer to that question is, yes, reliability was dominant in our minds, and we tried to test everything you can test. And you get to a point where you've tested something so many times that you've worn it out, and it's better to leave it alone. But, as I said, these failures happened with extremely subtle causes, none of which would have been revealed in a ground test. For example, on Ranger 2, the gyros in the Agena were not turning when it took off. Why? Because the blockhouse instrumentation was designed in such a way, no matter how much you test it, you can't tell whether the gyros are turning or not. Okay? Well, that was corrected, but we'd already lost one mission, so fine. The next Agena, the gyros were indeed turning, but we didn't have 50 missions the way you do in the Army. Okay?
Jim, in one of your slides, and concluding one, I guess, it was said that the politicians' invention of policy do not help, but probably worsen the situation, I completely agree with you because I just experienced it in my own career, But was it just the case in the Ranger program when the policy tried to assist you somehow, but actually interfere badly?
How did the politicians?
The politicians were faced with a problem that's very difficult for a politician. To us, it looked as if they were wasting their time and ours, but in their world, they really did have to consider whether we, happy engineers, who were just going along, always thinking we could make the next one work, and eventually we did make the next 3 of them work. Fine, everybody ended up a hero. So from an engineering standpoint, we did exactly the same thing we'd always previously done in the Army. You find a failure, you fix it, launch the next thing, it has a different failure, you fix that, and eventually you get to where you want to be. Okay, but Ranger was operating in a different environment. And the answer to Mikhail's question is, politicians could have done us tremendous damage because one question that arose, and it was treated in the aeronautical press then, is what's a university laboratory doing in this business anyway with a $60 million mission, 500 people working on it, big deal, So that question, had it gone the other way, had NASA not told the politicians to, hey, get off our backs, the JPL knows what it's doing, leave us alone.
Okay, thank you very much. We're going to have more time for questions at the end. Our next presenter is John Sarkeesian, who's going to talk about Mariner 2 and the Cicero Parkes Radio Telescope.
Wrong John. Oh, which one was that? Okay. Well, firstly, I'd first like to thank Bill Barry and the organisers for inviting me along here to address you this afternoon, and it really is a great honour, so thank you very much for that. The CSIRO Parkes Radio Telescope is one of the world's great research instruments. It is arguably the finest single-dish radio telescope in the world. In fact, in 2006, a study published in the journal Nature ranked it second only to the VLA in terms of its scientific impact. It is owned and operated by the Commonwealth Scientific and Industrial Research Organisation, or CSIRO, of Australia. And when it was built in 1961, it was the most advanced radio telescope in the world. It was also recognised very early on that its design made it a near ideal instrument for tracking spacecraft in deep space. This attracted the attention of NASA JPL, where it had its most profound impact in the design of the large aperture antennas of the Deep Space Network. As you can see from this table, the space missions that the Parkes telescope has been involved in spans the 5 decades of the solar system exploration, from Mariner 2 at the very beginning all the way through to the latest mission, Curiosity, just a few months ago. The highlight was undoubtedly the Apollo missions, from especially Apollos 11 through to 17. We also played a critical role in the Galileo mission to Jupiter, and also in the Huygens landing on Titan, where we actually were able to salvage the Doppler wind experiment through our observations. But how did it all begin? Well, it was conceived by Edward Taffy Bowen in 1954. Taffy was the visionary and dynamic chief of the CSIRO's radiophysics division for 25 years, from 1946 to 1971. Under his leadership, the radiophysics division developed as a pioneer and world leader in the emerging science of radio astronomy in the immediate post-war years. But by the early 1950s, Taffy was thinking of the next stage of development of radio astronomy in Australia, and he determined that the best all-round instrument for continuing the CSIRO's pioneering efforts in radio astronomy was a large, fully steerable dish antenna. At the time, such an instrument was beyond the budget of the CSIRO, so he called on his old boy network, so to speak, of contacts that he'd built up during the war to seek the necessary funding. Firstly, he approached the Carnegie Corporation. At the time, it was the president of the Carnegie Institute in Washington was headed by, the president of it was Vannevar Bush, who during the war was President Roosevelt's science advisor, the man who initiated the Manhattan Project, and he was also the founder of the National Science Foundation. And from his very close personal relationships, professional relationship with Vannevar Bush, he acquired $250,000 to get the project started. He then followed up with a similar amount from the Rockefeller Foundation. The president of the Rockefeller Foundation was Dean Rusk, the future Secretary of State in the Kennedy and Johnson administrations. Again, he knew Taffy during the war period. And Richard Casey, who was the man who actually set up the radiophysics laboratory within the CSIRO as a secret wartime laboratory, was a minister in the then Australian government and responsible for the CSIRO, and he managed to convince, and he was a great supporter of Taffy and of the telescope project, and he managed to convince the Australian Prime Minister to support it with matching funds. And then combined with additional private donations and with the additional funds from the Australian government and the Rockefeller Foundation to make up a shortfall towards the end of the project, he was able to acquire just over $1.4 million to build the telescope, which even in those days was considered ridiculously cheap. The telescope itself was designed by the Freeman Fox and Partners, a British firm. They were actually famous, especially in Australia, as being the designers of the Sydney Harbour Bridge. And they were contracted to design the telescope to CSIRO specifications, And the CSIRO engineer, Harry Minette, supervised the design of the telescope and its drive system from 1956 to 1959. This was much longer than they expected, but it paid off in the end because it meant that they got the design right. The telescope actually incorporated several very innovative design features. I'll just come to that in a moment. Firstly, it was pivoted in the centre. It's like an inverted umbrella, as you can see. It had an out-azimuth mount, which is unusual for its time for a structure that large. Also, in order for it to track objects smoothly across the sky, it incorporated a new invention of the master equatorial system. And it was basically just a small equatorially mounted optical telescope located at the intersection of the altitude and azimuth axes of the telescope. Essentially, the dish was slaved to that equatorially mounted optical telescope via a servo drive system that enabled it to very smoothly track objects across the sky. And finally, it had spiral purlins on the dish to give it strength. The site chosen for the telescope was near the town of Parkes, about 350 kilometres west of Sydney in the central west of New South Wales in Australia. And the reason it was chosen was because of those mountains in the background of the photograph there. They protected us from the radio emissions from the larger population centres further east, such as Sydney, for example. And so the area was a very radio quiet site, which was essential for a large sensitive instrument like Parkes. That young fellow there, standing next to the stake where the actual telescope was built, he's now 59 years old and he's a good friend of mine. He's the local farmer still. The main constructor for the telescope was MAN of West Germany. And so already you can see that it's beginning to take on the of an international project with the United States, Australia, the British and the Germans all involved in the construction. The construction itself began in late 1959, and over the next 21 months, when the Germans arrived to build the turret, they were able to weld the ribs into shape, and then they lifted them one at a time, bolted them onto the turret, and then when that was done, they then put the focus cabin up on the apex, and then panelled the dish. And as I said, it was all done in the amazingly short period of just 21 months. And that was and there was very little problems encountered in the construction, and it was mainly due to the time spent in designing it initially. The first tip of the telescope occurred in October 1961, and then mid-October 61, and then 2 weeks later it was officially opened by the Governor-General of Australia, Lord Delisle. The first director of the observatory was John Bolton. He was a legendary figure, a pioneer of radio astronomy in Australia, and he also, in 1955, moved to Caltech and started the radio astronomy program there, and founded the Owens Valley Observatory, which is which we had very close contacts with over the years. But how did we get involved in the space missions? Well, the story goes back to the period. The interest that JPL had in Parkes went to before even when the telescope was built. Began on the 6th of March 1959 when the US Army's Pioneer 4 spacecraft flew by the moon at what was then a record distance of 650,000 kilometres. And unfortunately, NASA JPL could not communicate with it effectively, even though it was a perfectly functioning spacecraft, because its small 26-metre antenna at Goldstone just didn't have the sensitivity to communicate with it effectively. And so JPL realised that what it needed was a much larger and more sensitive antenna than the 26-metre antennas that it was planning for its deep space network, or the fledgling deep space network. And so the requirements for such an antenna were that it needed to be 6 to 12 dB improvement over the existing 26-metre array they were planning, which meant that it had to be somewhere in the order of 60 to 80 metres in diameter. It had to have optimum performance at 2.2 gigahertz at S-band. In other words, the surface had to be extremely accurate. it needed to have a pointing accuracy of about 1.2 minutes of arc. And finally, it needed to have a slew rate of around 10 degrees a minute. And it was no surprise at all that these requirements matched the proposed Parkes telescope very, very closely. Consequently, during the tender and construction phase of the telescope, JPL made several representations to the CSIRO with the view of formally incorporating it into the Deep Space Network. Finally, however, a cooperative space exploration program was proposed, and you can see that it was for the occasional use of Parkes for data acquisition of a short-term nature where an extremely strong and reliable signal was required. And in fact, to this day, it is still the basis and rationale for Parkes' inclusion in space tracking operations. In 1962, a NASA research grant was awarded to the CSIRO to study the dish characteristics with a view to it contributing toward the design of the proposed JPL large aperture antennas. William Pickering, the JPL director, invited the CSIRO to participate in the feasibility studies and specification reviews of the JPL antennas. The grant also called for a detailed study to determine the performance parameters of the Parkes telescope in regards to those parameters you see there, the structural behaviour, characteristics of the drive system, radio frequency performance, vibration characteristics, but also measurements of the dish shape in the zenith and tilted positions. As a result of these studies, over the next few years, more than 30 research papers were published on the design and performance of the telescope. Parkes was not only the most advanced radio telescope in the world, it also became the most extensively studied. And the reason for it is because this information was considered to be of critical importance in the design and construction of the JPL antennas. The Caltech and JPL luminaries involved in that design were people such as Bruce Rule, Bill Merrick, Eb Recton, and so on, and they liaised very closely with the CSIRO engineers, Harry Minette and others, to ensure that the DSN antennas were operated as well as they'd hoped. Now, another aspect of the Parkes telescope impact on space tracking was in the location of the DSN stations. As you can see, the very first station was located at Goldstone, it was only just a few hours drive from JPL, but that then dictated where the other two stations would go. They needed to have their stations roughly equidistant around the globe, 120 degrees apart roughly, and so in the late 50s, early 60s, the other two stations were located at Johannesburg in South Africa, and also at Island Lagoon at the Woomera Rocket Range in South Australia. But for various reasons, which I won't go into, just lack of time, they had to shift the locations of those other stations, and one went to Madrid and the other went to the Tidbinbilla Nature Reserve, very close to Canberra, the Australian capital. And the reason Tidbinbilla was chosen was because Taffy Bowen was the chairman of the site selection committee, and he chose that site because Tidbinbilla was on almost exactly the same longitude as the Parkes telescope, because he argued that being on the same longitude, the two would see the same sky simultaneously, and that in the future NASA may want to link or array the dishes together to enhance the capabilities so that the two working together would be a much more powerful, more useful instrument than the two working individually. And of course that was realised some 20 or so years later with the Voyager 2 encounters of Uranus and Neptune, and also very critically with the Galileo mission to Jupiter. Now, it was during this design and study period that Mariner 2 was launched. As you all know, it flew by Venus on the 14th of December 1962, and it flew within just under 35,000 kilometres of the surface. Now, Taffy Bowen and Harry Minette decided that tracking Mariner 2 would be an excellent demonstration of the Parkes telescope's capabilities for communication at great distances. And essentially, the experiment would be a simple one involving the measurement of spacecraft position, signal level, and Doppler frequency. It did not include the reception of telemetry, but was simply intended to establish the technique and measure the performance of a 64-metre antenna. Parkes tracked it for 2 weeks, beginning on the 20th of December 1962 until the 3rd of January, when the signal was finally lost. JPL loaned Parkes an L-band transportable phase-lock receiver, which the astronomers dubbed the Ancient Mariner, as you can see, because it looked quite old even then, I think. But the thing that I found most amazing was that it had a 20 hertz gate that could be manually tuned. So the astronomers, they had to know the frequency very, very precisely and tune it to very close to the Doppler shifted frequency in the passband, and so they could get it in that 20 hertz gate and then lock onto the signal. Because these tracks were on an informal basis, JPL did not provide position and frequency predicts. So Harry Minette resorted to calculating these himself, using slide rule and pencil and paper. But he needed to know both the position and the frequency to lock onto the signal. He experienced great trouble at this, as you could imagine, because he was never sure whether the position was right and the frequency was wrong, or vice versa, or both. So eventually, after a week of fruitless effort, he contacted JPL, who sent him the predicts, and he immediately was able to lock on to the signal, as you see there. And here I found in the National Archives his hand-drawn plot of the results, and we just zoom in a little bit there. You can see that the Parkes telescope had an overall 5 dB advantage over the 26 metre antennas, in this case the one at Woomera, and it should have actually had an 8 dB advantage, but because a circularly polarised feed was unavailable, the astronomers had used the linearly polarised astronomy feed instead that incurred a 3 dB penalty. Nonetheless, the experiment was considered a great success, and the results were included in the study reports that verified the soundness of the design. And as a consequence of these, Parkes became the model for the JPL large aperture antennas. As you can see, they were all pivoted in the centre, just like Parkes. They had an out-azimuth mount, they incorporated the master equatorial system, and they were all 64 metres in diameter. The Goldstone dish was eventually commissioned in May 1966, but before then, Mariner 4 was flying by Mars, and the Goldstone dish was still a year away from completion, so Parkes was approached to provide the 64 metre capability for the DSN. 22 images were returned of the Martian surface, and Parkes provided a 3 dB improvement of the existing DSN array. In fact, all antennas combined, Parkes provided double the strength of that. The data from Parkes was combined with those from the other stations and used to produce improved images of the Martian surface, and you've all seen this one, the famous image 11, which made astronomers very, very disappointed because they were expecting to see verdant forests. Instead, they had a desolate lunar landscape. Now, perhaps the most famous mission Parkes was involved in was Apollo 11. No history of Parkes could be complete without a mention of its role. It began in October 1968 when John Bolton was visiting Caltech. He was invited to dinner at the home of Bob Leeton, a friend and colleague of John's, and one of the PIs for the Mariner 4 mission. Also at the dinner was Eb Recton, the head of the Goldstone project, and during the course of the dinner, John was asked if he could make available the Parkes telescope for the upcoming Apollo 11 mission, but in particular for those few short hours when the lunar module was on the lunar surface. And because human lives were at risk, both he and Taffy Bowen agreed. And as is well known now, 600 million people, 1/6 of mankind at the time, witnessed the Apollo 11 moonwalk live on TV through pictures received at Parkes. The story is far too long for me to go into detail in this short presentation, but I invite you to check the Parkes website and also the Honeysuckle Creek website for more details on that. And I think, oh yeah, it's just that there. And the beginning of the broadcast, NASA were just, TV's the thing that everyone remembers nowadays, but at the beginning of the broadcast, NASA Houston was switching between the signals being received at Goldstone and Honeysuckle Creek. When they finally switched to Parkes, it was so much better they stayed with Parkes for the remainder of the 2.5-hour moonwalk. And just to give you an idea of why they did that, on the right, no, sorry, the left, you have an image of Armstrong descending the ladder, sourced from Goldstone. 20 minutes later, when they were using the Parkes feed, you can see Aldrin coming down the ladder. You can see the improvement in the picture. Honeysuckle Creek had a very good image also, but because of its smaller size and lower signal-to-noise ratio, had a grainier image. The equivalent picture 20 minutes later, when Aldrin was about to step on the lunar surface, was from Parkes, and again you can see the improvement and understand why it was involved. Over the years, we've had a mutually beneficial partnership, the CSIRO and NASA. Whenever Parkes has supported a NASA space mission, we've gotten a better radio telescope out of it as a result. And in return, NASA has a more capable antenna for the next mission that they approach us for. You can see all the surface upgrades and the focus cabin and so on were all funded by NASA over the years, and we've got a much better telescope, and NASA has a more capable antenna for its next mission also. So in conclusion, I'd like to finish with a quote by the US Ambassador to Australia in 2003 when he was at Parkes to launch the Mars tracks. Tom Schieffer, and he said, to quote, "The Parkes telescope is like a trusted friend, always there when we need a hand. The relationship between CSIRO and NASA is very much like that between the United States and Australia. A friend that, as friends that share common values and dreams." And I have a picture there of the ambassador and the officer in charge of the Parkes telescope, John Reynolds, playing a spot of cricket on the dish during the opening. The ambassador had to learn how to hold the cricket bat correctly. He thought it was a baseball bat at the time, but it worked. And just to finish up, just 30 seconds, there is an epilogue to the story. On the 27th of August 1962, Mariner 2, the first interplanetary spacecraft, was launched to Venus. That just happened to be the day that I was born. Okay. And when New Horizons arrives at Pluto in July 2015, we could say, in all honesty, that in the space of a single human lifetime, the entire solar system would have been explored. And I think that's pretty impressive, and Parkes was there from the very beginning, so thank you.
I'm sure there are lots of questions, but we have time for just one right now.
Oh, we had a softball for it.
But my serious question is, I had not realized before actually that Parkes was, if you will, a prototype of these large steerable antennas. And what amazes me is that you got it right the first time in terms of critical things like the loading on the figure of the telescope. Was there some special innovation that enabled that, or was it just real attention to details and specifications?
It was essentially just the attention to detail, but also I didn't have time to go into great detail, but one of the engineers that provided the really innovative ideas on how it should be done was Barnes Wallis, a famous British engineer. He was famous during World War II as the inventor of the bouncing bombs. And it was his idea, essentially, to have an out-as-mounted telescope with the master equatorial. He invented that concept. And also the spiral purlins. He actually developed that idea for the R-100 airship and the Wellington bombers. And that's what gave the dish that strength. And it's also the reason why we've been able to upgrade the surface continually over the years, because that it did have that strength, and the designers of the JPL antennas were extremely interested in that, and they took a lot of those design features, as you saw, and incorporated it. With the added, they have to be able to transmit as well as receive, so they had a Cassegrain feed rather than prime focus as we do. But it really did come down to the designers designing it properly at the beginning, which is why they took their time and then built it quickly. It's a good case of hastening slowly, where take your time, design it, and then do it quickly at the end. And of course, they were the same people that designed the Sydney Harbour Bridge, and that's still up, and still will be for a century or two more, I hope. So,
Thank you.
thank you.
Our next speaker is Michael Neufeld from the Air and Space Museum to talk about APL and the Discovery Program.
While we're waiting for this to come up, I should just say, many of you, or at least some of you, know me as Von Braun V2 Peenemünde, and after 20 years of doing that, I said I have to find something else to do. I have kind of exhausted that line of attack, and I had begun thinking about several topics, and what I've hit upon, at least for the moment, was an interest in the entry of the Applied Physics Laboratory, Johns Hopkins Applied Physics Laboratory, which most of you in this room, being an insider audience, know is only 30 miles or 40 miles away, maybe less than that, on the way to Baltimore. The fact that I was a Johns Hopkins PhD had a minor influence on my interest in the APL, but it was mostly because Bob Farquhar, who couldn't be here today, was in our department and wrote his memoir. At least after he was in our department. He was supposed to do it while he was in our department, but that's another story. Bob always does what he wants to do. So what this project actually has moved into is two projects. One is on this Origins of the Discovery program, and the other is on the origins of the New Horizons mission to Pluto, which is an entirely separate topic, which I'll be talking about next year, I guess, when I go back to it. Well, of course, you already had some background here in previous talks, notably Mr. Callahan's talk yesterday with all those budget graphs, and he talked about the lost decade of the 1980s. And today, Arturo Russo mentioned some of the crisis and changes precisely in this narrow window of time that I'm going to talk about today. Of course, it is almost a standard narrative in the planetary scientists I've talked to about this topic, that there was a real sense of crisis at the end of the 1980s about this. Of course, you saw from the graph, from Callahan's graph, the lack of launches until 1989, although I should note that was partly an artifact of the shuttle disaster, and there might have been launches in 86, 87. But at any rate, there was certainly a period of decline or decrease in funding. What I found very interesting was when I phoned up Leonard Fisk, who was the Associate Administrator for Space Science from, I think, 87, I'm not quite sure exactly what year, 87 to 1992. He gave a completely different picture than what the planetary scientists, notably Wes Hunters, who I've talked to, and one of my chief characters, Tom Cremegis of APL. He said this was a great period of expansion. He came in, the budget of NASA started going up as a result of Reagan and then of Bush, first Bush, at least in the late 80s and the 90s. He pointed out that there had been an agreement made between the NASA administrator and the SSB that 20% of the budget would be allocated to space science. This agreement was made in 1984. It was a result of the near death, which was described, the planetary program and the general reduction in the space science program at the beginning of the 80s, and after NASA had survived that, SSB was promised a 20% budget. So NASA's budget was going up, and therefore the Office of Space Science and Applications, as it then was, that budget was going up very quickly at that time, and there were a number of missions in the queue delayed by the shuttle disaster, which were on the imminently going to be launched, notably Hubble Space Telescope, Galileo, Magellan, Ulysses, all were going to be launched. And so as far as Len Fisk was concerned, this was not a period of gloom and doom at all. This was a great period. Of course, he was the period coincident with him being AA, but so this is a period actually when things were started going really well and there was an expansive budget. Certainly this wasn't the feeling that the planetary science community felt at the time because of the lack of launches, because of the gap. And one of the responses to this was, do we need a small spacecraft program, particularly in view of the failure of the Observer line and Mars Observer in particular to live up to its budget requirements. Now, I know that there's a little argument actually about whether the Mars Observer narrative that we usually hear, namely that it was just a program out of control and too expensive, was really the case. I mean, Eric Conway, among others, has noted that part of the big budget increase for Mars Observer was that it had to be delayed an entire Mars launch opportunity from 90 to 92, and that greatly added to its cost. But at any rate, there was certainly a sense then that there was a need for some other smaller missions to increase the flight rate, to increase the amount of data coming back to deal with the problem with these gigantic, expensive flagship missions which were eating up the entire budget. Now, as far as I can tell from the documents that I've been able to so far find, the initiative for a new small spacecraft program started with Jeff Briggs, who was the division director for planetary sciences, then called Solar System Exploration, and that SSED means Solar System Exploration Division, in the spring of 1989. And he actually created a small initiative, and it was part of the strategic planning that OSSA was making at that time. And Len Fisk told me probably that he thinks he invented the idea of strategic planning at NASA for mission planning. At any rate, there was a strategic planning process going on in OSSA in 1989. And one of these workshops that was coming up was at the University of New Hampshire in June 1989, and so that this small program initiative was going to be discussed there. But there was a lot of hostility in the community as well, or at least skepticism in the community about a small mission program, because the basic message was, well, we tried it with Observer and it was a complete failure, so why should we try another small mission program? We can't control costs. Planetary missions just cost hundreds of millions to billions of dollars, so there's nothing you can really do about that. And others have mentioned already this problem of piling on. Everybody says the last bus out of town, therefore we all have to get our instruments on it. Well, the early idea for a small mission was actually converging on the idea of near-Earth asteroid rendezvous. We've already heard in several presentations mentions of the fact that asteroid missions and asteroid rendezvous were constantly under discussion in this period, and there was the more ambitious Comet Rendezvous asteroid flyby craft mission to be combined with Cassini program at the time. But it would appear that a near-Earth asteroid mission, which was relatively low energy and low complexity, might be a good candidate mission for a small spacecraft. However, again, there was this hostility or skepticism in the planetary sciences community. And that's where first of my, two key actors, one, the other being Wes Huntress, I'll talk about who's here, is Tom Cremegis of APL. And this is a picture of Tom Cremegis, this is an audience I mostly don't have to introduce him to, but he's a very eminent space plasma physicist, student of Van Allen, had experiments beginning as a postdoc at Iowa, a doctoral student and a postdoc on Mariner 4, and and I think he's there. I don't know who these other gentlemen are. Somebody in the room might be able to tell me. I think this is the low energy charged particle experiment. He was the principal investigator for LECP on the Voyager mission. So he had a position of considerable influence in the area of space physics as a student of Van Allen, as a very successful PI and co-I on many, many experiments to virtually every planet. And he says when New Horizons pass Pluto, he will become the only scientist who has had an experiment that has gone to every single planet. I can't verify whether that's true or not, but it's probably true. At this point in time, Tom Cremegis, or Stamatios, as his Greek name is, was the chief scientist of APL Space Department. And I should say something about APL Space Department here for context. Although in this discussion, in my paper, and everybody else has written about APL and JPL and a competition between two institutions, in fact, it's not the competition between JPL and the entire APL, which always has been a predominantly Navy-funded laboratory, but between Space Department, which was actually only at that time about 10% of APL's complement of around 3,000 people. The Space Department had built its reputation and history on the transit program for the Navy, and then had been involved heavily with SDIO missions in the 1980s, And as we transition into this period, is actually looking essentially for a new, would be transitioning again under the leadership of Cremegis, who became head of Space Department at the beginning of 1991, to having more NASA missions. So it had done significant numbers of heliophysics type or Earth orbital spacecraft missions. At the New Hampshire conference in June 1989, Cremegis intervened in one of the discussions about what kind of low-cost program could there be, and his intervention was, you guys are looking at the wrong model. It's not Mars Observer, it's the Explorer program. The Explorer should be the model for what a small spacecraft line should be, not only in its constant level of funding, but also in a small spacecraft as constrained cost and science focus. And he was challenged to present something to demonstrate how that could even be possible. And he called his secretary, had her fax up the view graphs that had been made for ACE, the Advanced Composition Explorer, which actually was launched in 1997, that APL was going to build, and presented, and this is actually a page from the fax that was sent up to New Hampshire, in the presentation of view graphs that he made about this. And I just want to read from an oral history because it tells the story much better than I would ever tell it. He said, it had all the ingredients, this is his Tom Cremegis, all the ingredients of planetary spacecraft. It had a rocket engine, it had the instruments, it had the orientation, it had the solar panels. Then at the end, Joe Viverka, who was chairing the session, said, all right, Cremegis, how much does that cost? I said, you guys seem to be experts in cost. You tell me, what do you think this mission should cost? He said, $400 million. I said, you're in the right ballpark for the spacecraft, except you have 1 zero too many. He said, what are you talking about? I said, the spacecraft is actually $45 million and the instruments another $30 million. So at least in his telling of the story, this is the origin story of Discovery from Tom Cremegis' perspective, that coming out of that workshop, they decided, indeed, well, at least we should study that. Study the concept of a small spacecraft mission, maybe based on an Explorer model. And I think it's interesting that Tom Cremegis is a participant in both the planetary sciences community and the space physics, are now called, most likely called, heliophysics communities, and he had this dual disciplinary perspective which allowed him to look across lines that the planetary scientists hadn't known much about Explorer, he said, to his great surprise. So in fiscal year 1990, Jeff Briggs started the Discovery program, created a Discovery Science program, science working group, named Bob Farquhar, who was at Goddard, to be the program chief, program head, at least part-time, of this little program. The science working group held 2 meetings, and yet somehow the NEAR concept, which had emerged from the New Hampshire workshop as the probable next mission and a way to go, didn't really go anywhere. And it's a long story, and I'm going to take up way too much time here to talk about it. But it does seem to have languished during the year 1989-1990. One theory that I have is that a lack of a sense of urgency from the top, from Len Fisk and others at the time. Things seemed to be going well. There was lots of money. Was this urgent? Maybe not. Another question is whether the creation of Bush's space exploration initiative, which caused the replanning process in the planetary program to consider what we're going to do to support a human mission to Mars, might have resulted in a distraction. But at any rate, not much of anything happened during that fiscal year, and NEAR was not funded as Tom Cremegis had expected. Now, of course, we have Wes Huntress who's sitting here, so it's an interesting experience. I'm used to writing about dead people or Nazis that won't talk to me. So it's a little intimidating to sit here and talk to the participants, but anyway. Wes Huntress became chief of SSED in August 1990. Replacing Briggs, and Discovery, as he said in a set of 3 oral histories that I have with him and in a phone conversation we had, Discovery was one of his 3 major objectives. Interesting enough, one of them was extrasolar planets. He initiated an extrasolar planetary program out of the Planetary Solar System Exploration Division. And he decided that in order to revive this initiative, which seemed to be languishing, he revised the Science Working Group, put Joe Vaverka in command of that, or in leadership of that. He created a technical committee, Jim Martin of Langley, legendary manager of Viking, as the head of a technical community, and said, go out and try to get this thing going and go somewhere. At this point in time, at least by Wes Huntress's account, he basically was looking at the options. Who could be a competitor to JPL? And this is a story that is, unfortunately, all our JPL friends in the room, is not entirely flattering to JPL, because the perception that he had and several other people, and Tom Cremegis had, was the place was very wedded to giant, expensive projects, could not adapt to a small, low-cost mission, was very resistant to any other organization having any piece of its turf, was very afraid that some other organization would come and steal its charter. And so was very resistant, and Huntress looked around, and what are the options? NRL was an option, but they didn't seem terribly interested. Sorry, our friends at Ames, but he's told me, or told several oral history interviews, he didn't have much confidence in Ames anymore and ability to do an interplanetary mission. And that left APL as one of the most likely candidates for a competition, a competition whose project was maybe not only to get Discovery started and to do a good near-Earth asteroid mission, but also to give JPL a shaking up and a motivation to do better on small programs. So this led to the funding of the NEAR project in fiscal 1991, and a showdown that happened in Pasadena in May 1991, APL versus JPL NEAR. This is an early NEAR sketch, NEAR proposal idea. The outcome of that was rather a legend at APL and forgotten at JPL, because basically JPL's proposal was a disaster, and was proposed for a $450 million program that would monopolize Discovery for a decade and take 3 missions just to get to the asteroid. And APL proposed a $110 million mission. And so Huntress decided to pick APL, although it's interesting, I'm talking too long, I'm running out of time to tell the rest of this story. But he decided, in part because the superior proposal was APL, even after JPL got a second chance. But it was also because he was looking for a way to stimulate JPL to think about doing something new and to try it a different way. And he has specifically picked out Tony Spear, who had been project manager on Magellan, has saved Magellan, to run a small project office. At the time, this NEAR mission seemed like it should go to APL. He picked APL, so he decided to create a lunar mission called Lunar Scout. But unfortunately, shortly after Lunar Scout's creation, it was stolen away by Mike Griffin, who had just been appointed the head of a new Codex for exploration to try to revive the Bush Space Exploration Initiative. And so OSSA lost the moon for a little while Codex existed, which, as he said, and I quote, "that really pissed me off." So there's an oral history, there's an uncensored oral history. I like that. So he decided we got to find a Mars mission for JPL, some way, and of course there are already, there's a lot of other things going on, which Eric Conway has a history in the works about that. And so out of this came the Pathfinder proposal. And there was an AIM study for so-called Measure Mars Environmental Survey mission, and there'd be a Pathfinder mission to a network, and all of that. And let me summarize more quickly here. A micro rover was added, and at the end of this process, which sort of happened during the winter of 91-92, his decision was to incorporate the Pathfinder into Discovery. It was the basic measure for Discovery had been decided. It would be $150 million FY92 project This would have to come under the $150 million cap, but the rover was counted as a separate thing. It came from a different part of NASA, and it was extra. And that was the decision then, that his decision was to make Pathfinder first and to push NEAR into the background. To push NEAR to, not in the background, but push NEAR to second. To push it off out of being the first in line, which did not make Tom Cremegis happy at all. And so this would bump the NEAR launch, which had been scheduled for 1997, into 1998. This is, of course, now we're talking about 1992. But the funding for Discovery could not happen until the next fiscal year, so it would not come up for budget consideration until the spring of 1993. And so essentially there was a year where APL, which was ticked off by this sudden demotion to second in the Discovery program, didn't come about into a political consideration. However, Tom Cremegis told Bob Farquhar he should go look for other options, and they found another option. They found a launch to Eros in early 1996. This would, in fact, greatly accelerate the program, result in APL having to produce a spacecraft in only 2 years. Pathfinder was still first in the budget consideration when it came up in 1993, and NEAR was at best minimally funded in that year, but Tom Cremegis was not about to take that lying down, basically. And the reason that he was able to do anything at all was because he had a long history of close association with Senator Barbara Mikulski in using the political system to lobby for APL's projects. And he intervened directly with the office of Senator Mikulski, who then changed the whole dynamic. The budget consideration of FY93 would have funded Pathfinder, basically, and NEAR on a very small budget for a 1998 launch. Instead, by using the political system, Tom Cremegis was able to get Mikulski to insert into the bill the full funding for NEAR on an accelerated launch schedule to reach Eros by launching in February 1996. And as a result of that very abbreviated version of that history, the Discovery program started in the fall of 1993 as a much better funded program with 2 full New Start missions than it would otherwise have been. And one of the questions we have to ask is whether it might have resulted, if it had not been funded that way, would it have become a 1-mission program for Pathfinder? Wes Hunter says, well, at least Golden was really only interested in Pathfinder and didn't know much about NEAR. At the very least, Discovery became a viable program at a higher funded level early on. And so I would say my fundamental interpretation that I've offered in this paper is, although Jeff Briggs had a role in starting the project, that the 2 key actors which made it happen were Wes Huntress and Tom Cremegis, and without them, Discovery might not have emerged at all, and certainly led it to become the successful and transformative project for planetary exploration that it has become. Thank you very much.
Time for just 1 or 2 quick questions. Oh, from the very alive Wes.
Speaking of participants talking to my paper.
Is this thing dangerous?
Just a comment.
Yeah.
On your last slide there. Dan Golden and I were not unaware of what the final outcome might be. We were actually happy to see it happen that way.
Which final outcome you mean?
That we would get a new start for 2, not just 1.
Yeah. But in one of your oral histories, you say that that he was really angry because of Mikulski's intervention.
He was.
Yeah, he was. Yeah, I know, you weren't, yeah. I mean, I should add as an appendix to that, I have not mentioned Golden in this talk for the very simple reason that he actually doesn't deserve much credit or blame or anything else for this. This is a project that became the keystone of Faster, Better, Cheaper was launched without him, and his basic contribution was to stay out of the way. Now, maybe in later years you could argue, it would not have necessarily continued without the continual support of an administrator who wanted to keep it going. So. That's probably a contribution.
This is really more of a comment than a question. That was a lot of fantastic background that I have wanted to have for years. And I'm coming at this from the perspective of somebody who's been involved with Discovery almost since its inception, but not that far back. In 1996, I was asked by Charles Alachi, who was an assistant director of the lab, to head JPL's Discovery program. And I knew about APL. I knew what a formidable technical powerhouse they were. I'd heard about Tom Kremegis, and I knew about Barbara Mikulski's special relationship with him. And so we took that competition extremely seriously. In fact, I think Alachi asked me to do that job because I was the PI on an earth science mission about the size of an Explorer. But I'll tell you this, at the lab, my friend said, "Greg, why are you doing this? This is a dead end. You know, it's the flagship missions that count. This Discovery thing is never going to last." That was the attitude there for quite a while. And now I can tell you that today, I just passed the reins to someone else after InSight was selected. It's a core part of what we do at the lab. And not only that, but it has also had a very profound impact on how we do strategic mission planning in terms of the way we formulate them. We have fallback options, we have more robust reserves, we have baseline payloads, we have the threshold payloads, and we also have a review process over the strategic missions now that we never had before, and I think it's really going to help us keep them on track in the future. So I think the ramifications of Discovery are far beyond what we might even think today.
Yeah,
So
certainly
thank
had
you,
this
Wes,
planning
and
dimension
Tom.
that's been important in terms of PI-led missions. Thank you.
Thank you. Final paper this afternoon is from Peter Markovsky from University of Oklahoma on a subject near and dear to my heart on the International Solar Polar Mission.
I just wanted to make a quick note. On the program agenda, I originally wanted to talk about Ulysses and Giotto, but my paper and my project sort of evolved to only just talk about Ulysses. I think in kind of grander scheme of things, I'm going to fold Giotto in there. But for today, I'm only going to focus on the history of Ulysses. In May 1987, former ESA director Reimar Lust, upon reflection on American and European cooperation in space, emphasized, quote, the importance of a free and open exchange of views between the scientific communities of the United States and of Europe, end quote. He further stated that it is true, and we should never deny the fact that we live in a world of conflicting, or at least divergent, political and economic interests. But in spite of that, I do believe that many of our present problems can be solved more easily when there is an international community of scientists and scholars free to follow common goals and common objectives. His reflective statements are perhaps in light of the tumultuous period of cooperation earlier in the decade, involving the collapse of the original agreement on the International Solar Polar Mission, ISPM, in 1981. This mission would reemerge as Ulysses later in the decade, and by the time of its launch in 1990, it would cap an almost three-decade journey from its original conception as an out-of-ecliptic, or OEE probe, in the early 1960s. Today, I hope to show you how the history of Ulysses, the Ulysses mission, can be reframed within a new emerging historical literature, which attempts to marry the history of space within a transnational framework to perhaps tell a more globalized narrative of space exploration. My work is an attempt to build upon what historian Asif Siddiqui proclaims as the issue of multiple and contradictory narratives engendered by national claims which have been a staple of space history. While these nationalistic and even Cold War contexts have certainly had a tremendous influence upon the American and Soviet programs, what about those ones which matured in the post-Cold War era, such as the Chinese, Japanese, or Indian programs? Or programs like ESA, which emerged in the same period amidst larger concerns of European political integration? In the following talk, I will detail the 25-year history of Ulysses, from its origins as a proposed OOE mission to its launch in 1990. In doing so, I will attempt to reframe the history of Ulysses in transnational perspective and show two things. First, I will demonstrate that the spacecraft itself can be seen as a transnational object. That is, it's a transnational form of cooperation is embedded in the technology itself, which was negotiated and shaped by the multitude of American and European historical actors over its 25-year history. Second, and more importantly, in detailing this history from the perspective of a number of historical actors, I will show the emergence of the varied meanings and imaginings of cooperation amidst the larger development of the joint mission. All right. So shortly after the launch of Sputnik in 1957, space scientists began to discuss the advantages of utilizing spacecraft for a number of scientific investigations. Almost immediately, scientists on both sides of the Atlantic began to pursue solar observatory capabilities. These scientists began to coalesce and develop new and interesting strategies for solar exploration, one of which was an out-of-ecliptic mission. By the early to mid-1960s, a number of developments from both European and American scientists and engineers occurred. In Europe, two champions emerged. German astrophysicist Ludwig Biermann of the Max Planck Institute and British space scientist Harry Elliott of Imperial College. Biermann's contribution included the first publication to consider the scientific value of an OOE mission. The second champion, Elliott, was one of Britain's leading authorities in space science in this period. As an appointed chair of the British National Committee on Space Research's Working Group 3, he successfully steered his committee to the conclusion that an out-of-ecliptic mission would best meet the dual necessities of yielding novel scientific results and stimulating the nation's aerospace industry. From 1968 to 1971, he had mixed success regarding support and interest for an out-of-ecliptic mission, but ultimately his efforts resulted in the April 1982 European Space Research Organization, or ESRO's, mission definition study. By the early 1970s, there were parallel developments amongst NASA and American space scientists regarding the feasibility of such a mission, as it was also seen as a potential candidate for NASA's emerging planetary exploration program. By this time, American scientists and engineers were already developing solutions for issues that a possible OOE mission might face, and by extension, technical issues facing future interplanetary probes. While not as complete as the ESRO study, in July 1971, the Ames Research Center published the Pioneer H Jupiter Swing-By Out-of-Ecliptic Mission Study. While the report outlined a number of different launch and hardware configurations, the proposed Pioneer OOE would use the spare Pioneer spacecraft for Pioneers F and G, which would eventually become Pioneers 10 and 11 respectively. For the next few years, attempts by a number of American scientists to persuade NASA administrators to use the backup Pioneer probe for an OOE mission went largely unsuccessful. While a number of administrators recognized the potential benefits, a few concerns arose regarding its use. Writing to John Nagel, Norman Ness, the chief of Laboratory for Extraterrestrial Physics at Goddard, expressed concerns about the use of a backup Pioneer. According to him, an OOE mission seems like an exceedingly worthwhile mission scientifically, and perhaps a backup Pioneer probe might not fully capture the potential of an OOE mission. At his behest, he urged its adoption only if the payload be entirely reconsidered. In response, Nagel cited budgetary and time constraints regarding the solicitation of an entirely new spacecraft. About a year later, in August 1972, Homer Newell expressed another concern regarding the use of a backup Pioneer probe for an OOE mission. His suggestion was to keep Pioneer H as a backup in case Pioneer 10 would not provide sufficient data regarding issues like radiation environment of the interplanetary space. By mid-decade, NASA administrators would continue to solicit advice regarding an OOE mission. But as we have seen in yesterday's talks, which highlighted budgetary concerns in this period, NASA, as a result, became increasingly supportive of a joint international mission. American scientists' reactions to such a joint mission were varied. By summer of 1974, some expressed concern about the perceived lack of consultation within the scientific community. John Simpson, physicist at the Enrico Fermi Institute, wrote to James Fletcher in 1974 expressing the importance of an OOE mission. He stated, "I was shocked to learn when I was in Italy that NASA had invited the European Space Group to consider taking over this type of mission. I find this incredible since I can think of no other mission which would guarantee as many scientific discoveries per dollar spent on a major mission than this one. Thus, this potential reduction of participation by U.S. scientists is hard to justify within the United States, both for strengthening U.S. science at this time and for NASA's stated objective of supporting U.S. science. This mission is outstanding. I am just strongly enough oriented towards strengthening U.S. science at this time to argue that this should be an all-U.S. mission, if possible. Nagel recognized by mid-decade that while U.S. scientists were increasingly concerned about the idea of international cooperation, Congress, on the other hand, was becoming more interested in the idea of cooperation in space missions in general. According to him, Congress views such cooperation as a reduction in funding requirements, whereas the U.S. scientists regard such missions which will carry U.S. and foreign experiments as a reduction in their own opportunities to do research. In the tight budget climate for space science, two different concerns from two different groups seem to place their opinions at odds. To Nagel, and perhaps to other NASA administrators, cooperation would actually be a good compromise for all parties involved, as collaboration would produce a net increase in the number of flights and hence a net increase in the total opportunities for U.S. scientists. Moving on. By the end of 1974, two main developments led to what would eventually become ISPM. In Europe, as ESRO was considering mission priorities for the 1980s, a stereoscopic mission to study coronal phenomena emerged as a compelling and worthwhile candidate for a future mission. ESRO's Launching Program Advisory Committee, LPAC, included both an OOE and a stereoscopic mission as top priorities, which led to the second development, the combination of a stereoscopic mission and an OOE one. And this essentially proposed that the out-of-ecliptic mission would use you would launch two satellites, one which would fly over the North Pole of the Sun and another one which would fly over the South Pole. NASA seemed to agree, and according to James Fletcher, the best chance of implementing an out-of-ecliptic mission is with a mission mode that will attract as wide a constituency as possible, something that a combined stereoscopic and OOE mission would do. These developments created a ripe atmosphere for cooperation. In 1974, ESRO and NASA agreed to cooperate on two joint missions at the Joint Science Program Review held at ESTEC, and one of the agreed programs was the combined stereoscopic OOE mission. Combining two such missions was very favorable to both NASA and ESRO administrators, and as a result, a science working group was established in order to form an optimum mission mode. In the first few months of 1975, based on the joint study, ESRO and science planners recommended that an OOE dual stereoscopic spacecraft using a Jupiter gravitational assist as the most suitable candidate for cooperation. As historian Karl Hufbauer has shown, ESA, which replaced ESRO as Europe's prime space organization in 1975, emphasized a number of priorities for the cooperative OOE mission, such as clean interfaces, their involvement in the choice of experiments and principal investigators, observations of Jupiter, their insistence on observations of Jupiter be made during the swing by, and the conviction that the two spacecraft option remain essential. Overall, by mid-decade, the mission constituency for an OOE mission became broader, larger, and more diverse. In April 1977, NASA and ESA began soliciting proposals for an OOE, and by March 1978, a total of 16 experiments were chosen for more than 200 scientists belonging to 65 universities from Europe and the United States. While the specific technical and scientific capabilities of the OOE mission were developed from 77 to 78, securing funding for the cooperative mission was increasingly becoming a problem. For instance, in May 1977, NASA was scheduled to take a $77 million cut to the fiscal year 78 budget. This had a particular impact on the planetary missions program, especially for the newly planned Jupiter orbiter probe. In July, the House of Representatives approved $17.7 million for the Jupiter probe, and as a although they had a stipulation, and that was that the upcoming planned start, 1979 planned start for OOE would use a modified version of the Jupiter orbiter probe. So thus, the fates both of OOE and the Jupiter orbiter were connected. With this new budget approval for the orbiter, the OOE mission plans would have been, without the new budget approval, the OOE would have been threatened. Requesting more funding for the out-of-ecliptic mission, which by late 1977 was renamed as the Solar Polar mission, was becoming increasingly difficult. In September 1977, NASA secured authorization from the OMB from ONB for an initial fiscal 78 budget of $13 million, arguing that it was their only new start for that year. Despite these issues, 1 year later in 1978, after intense lobbying efforts of the American space science community and Harold Glasser, the first director of the NASA Solar Terrestrial Division, Jimmy Carter officially approved the solar polar mission. 6 months later, on March 29, 1979, NASA and ESA signed the Memorandum of Understanding for the International Solar Polar Mission. As was seen prior to the signing of the MOU, ISPM was already facing budget issues. In January 1978, NASA submitted a budget request for fiscal year 79, which included $13 million for ISPM, claiming it was one of their 5 New Start programs for that year. Although Congress approved it, they cut $5 million of that budget in order to reallocate those funds to cover cost overruns for the space shuttle development. By the end of the year, the Senate Appropriations Subcommittee wrote to NASA Administrator Robert Frosch suggesting that ISPM be delayed 2 years, citing 2 reasons: to reflect the delays in shuttle development and because the committee was concerned with the inertial upper stage necessary to send the 2 spacecraft on the flight path would not be adequate and that NASA should develop a high-energy upper stage instead. Despite $135 million worth of contracts already promised by this point, ISPM was teetering on the edge of cancellation as the Carter administration submitted an amended budget in fiscal year 1981, which called for a 2-year launch delay and roughly $43 million cut. The cut and delay urged protest by a number of groups, which included not only European nations, but also the White House and State Department. White House officials, in a letter to Massachusetts Representative Edward Boland, claimed the action threatens not only international cooperation in space, but other areas of technology as well. A few months later, the House Appropriations Committee recommended in the 1980 Supplemental Appropriations Bill that ISPM be canceled, citing among other reasons that the 2-year delay would cost at least an additional $150 million. While ESA reacted to the possible cancellation with strong diplomatic protest, Florida Representative Don Fuqua successfully argued that the cancellation of the funds would constitute legislation in an appropriations bill, a violation of House rules. As Joan Johnson Fries has shown, the fate of ISPM took a turn for the worse in the early 1980s, as the whole budget process and attitude fundamentally changed with the election of President Ronald Reagan and his appointment of David Stockton as director of OMB. By early 1981, it became clear that the Reagan administration's proposed budget cuts for NASA would effectively cancel ISPM. After Reagan took office, OMB amended the fiscal year 82 space science budget by almost 23%. This move effectively signaled the cancellation of the development of the American portion of ISPM. The swift and almost unilateral decision by the Reagan administration elicited uproar from both American and European delegations. American politicians decried that a lack of New Start projects could jeopardize the ability for NASA to keep its status as a scientific and engineering leader. ESA individuals responded by declaring the decision to be an unacceptable breach of the Memorandum of Understanding. As a response, NASA and the Reagan administration offered vague reassurances that the U.S. would remain as part of the ISPM mission at a reduced capacity, which Europe viewed as unacceptable as well. By March of that year, ESA assembled its political forces against this decision. Director General of ESA at the time, Eric Quisgard, stated to the House Science and Technology Committee that it cannot be accepted that at such an advanced stage of ISPM development, and after a commitment of more than half of the European funding, NASA presents ESA with the fait accompli of its withdrawal from an international cooperative program, especially without prior consultation. He further went on to tell the committee that the short-term financial advantage for NASA might come at the cost of potential future cooperative ventures. In the following weeks, Quisgard and ESA expressed willingness for a compromise solution, as long as the U.S. was willing to reinstate its spacecraft. Despite some promising efforts in the early summer of 1981, newly instated NASA Administrator James Beggs informed Quisgard on September 9th, quote, that NASA would not include any request for funds for the second ISPM spacecraft in the fiscal year 83 budget. He did offer support and encouragement for ESA to pursue a single spacecraft mission, in which NASA would fulfill any remaining commitments. By the end of the year, the dual spacecraft ISPM mission was officially out of commission. Despite the cancellation of the U.S. craft, ESA decided to continue with the Solar Polar Probe, citing a substantial commitment already made thus far. In the early 1982, ESA sought continued assurance from NASA and Congress. They also made a point to stress in their discussions to develop and establish a framework for future cooperative ventures, the start of what Johnson Fries characterizes as a strategy that ultimately made ESA a stronger, autonomous, and more independent space agency. Moreover, in July 1984, ESA announced the renaming of ISPM to Ulysses. While they suggested the name change was chosen to reflect the hero in the Odyssey and a reference to Dante's Inferno, perhaps this name change also reflects a long, arduous journey of development. While it was scheduled, while the Ulysses was originally scheduled to be launched in May 1986 aboard the space shuttle, the Challenger accident delayed further launch indefinitely. A new launch date was eventually chosen after the restoration of the shuttle program, and Ulysses was finally launched as part of STS-41 on October 6, 1990. So what makes the history of Ulysses transnational? To start, I would like to suggest that the main technological component, the spacecraft itself, is an example of a transnational object. By this, I mean that the mission and the spacecraft was negotiated along transnational lines, in which a host of actors and institutions helped to shape the technological component itself. That is, its development into what it eventually became was a result of a number of different factors and lines of cooperation from both European and American space agencies. Finally, I would like to conclude with another aspect of Ulysses' history that benefits from this perspective. The approach that I have taken highlights the changing meanings and imaginings of cooperation and collaboration between the various actors and organizations, such as the number of individuals at NASA and ESA, as well as the number of scientific and engineering communities. It seems at different times, different individuals saw different sets of values, or perhaps no value at all, in cooperation on an out-of-ecliptic mission. Furthermore, Ulysses provides an interesting case study for such an analysis, as it complicates the nature of cooperation in the sense that it was a failed project, as its original conception as a dual spacecraft mission dissolved. Yet, while the original vision of a cooperative ISPM mission failed, the project lived on, both in the sense that an actual material object was created, Ulysses, and the Ulysses probe and the Ulysses mission continued, albeit in a different form. In this light, I would like to ask the question, what exactly is a failure? While the ISPM mission was never launched, some form of an OAE mission did eventually make its journey around Jupiter and towards the Sun. While I do not think I can provide a concrete historical answer as of yet, I think in reframing Ulysses in this way, hopefully I could tease out some of the more interesting and nuanced aspects involved in failure more generally in space exploration and cooperative ventures in space exploration. So to conclude, hopefully I've demonstrated why and how adopting a transnational perspective might enrich our understanding of international cooperation in space exploration more generally. While I've only scratched the surface in this paper, I believe that ultimately adopting this perspective might help us understand the multiple, imagined, and varying meanings of collaboration constructed by both NASA and ESA. Thank you.
We'll have all the panelists so that you can ask your questions. Encouragement? Oh, I'm sorry, I can't see over here. Sure, go ahead.
No worries. Thank you. Yeah, this is for the last speaker. Thank you it was a fantastic presentation. I wanted to ask a little bit, or push a little more, allow you to expand a bit on the notion of a transnational object, particularly as distinct from, say, a boundary object, and especially in the light of current trends in transnational theory and anthropology, for example, that would inspire us to step away from any idea that nation states are necessarily the boundaries by means of which national or transnational collaboration should be understood, and how that's particularly tricky in the case of space missions when you have these large institutions that are bound up in national frameworks, but also especially that represent national interests. And I'm wondering how looking at, say, the Ulysses as a transnational object inspires us to break apart perhaps our notions of the singular, for example, European Space Agency, et cetera.
Yeah, so in the longer story, I didn't outline it in the paper, I mean in my talk, but in the paper, there are a lot more discussions, particularly about the specific components. One such thing was kind of the engine component. And RTG was eventually used for Ulysses. But I think that in focusing on these discussions, which were within the specific communities themselves, so they weren't necessarily discussions amongst administrator to administrator, but these were the different scientific communities arguing, well, this configuration is better, or this configuration is worse, or something along those lines. I think of sort of prioritizing the sort of top-down view less and kind of teasing out these smaller kind of arrangements and arguments and discussions. It won't necessarily completely push out the national context, but it won't prioritize it as a kind of major focus.
Right. Thank you.
Yeah, did the collapse of the Green Bank telescope create concerns at Parks? The radio telescope at Green Bank had the rather spectacular collapse a few years ago.
1988.
Yes.
That one. Yeah. Well, that was actually, that's a good point, because the Green Bank, I think it was the 120-foot telescope that collapsed, was put together very rapidly for a very designed to be used only for a very short period. And then, but it was continually extended, of course, and it was a transit instrument, and it failed from metal fatigue and so on. But the Parkes telescope was designed to have a lifetime of about 20 or so years, and last year we celebrated the 50th anniversary, and with the new upgrades we're doing, we're going to probably continue for many more years to come. But no, I think a lot of the users of the Parkes telescope were users of the instruments at Green Bank, the National Radio Astronomy Observatory in West Virginia, and there were always a lot of close ties between the two radio astronomy communities, and I think at the time it came as a profound surprise. I know it came as a surprise to the observer at the time. He just was not expecting that. I hope it never happens to Parkes, because the control room is directly under the dish, and so, but yeah, but the replacement of it, the 110-foot Green Bank telescope, is a magnificent instrument, and I certainly hope that it's able to continue. I understand that it's under some threat because of the reassessment of its funding and so on. But it really is a magnificent instrument, the replacement for the one that collapsed, and as I said, I hope it does continue.
Yeah, Torrance Johnson. This is just a further comment for Peter's excellent study on the Ulysses. International issues. And what I find interesting is, despite the natural angst which you've described between the communities involved, because everybody felt, if not betrayed, at least not dealt with fairly by each other's governments and so forth. Within a few years, we were actually cooperating, as you point out, on a number of things. Interestingly enough, one of the most important cooperations was on the return to flight launch schedules, because as they got the shuttle going again, both Galileo and Ulysses wanted to launch in the same opportunity. They're going to the same place, Jupiter, so the windows were the same. And as it turned out, it fell to Peter Wenzel, who is the project scientist for Ulysses, and myself, to work with our individual project science groups to try to develop the arguments as to who should go first, because Admiral Truly said, I can't launch you both in the same month. That puts too much risk on getting you guys back into space. And we did that very amicably, with both of our PSGs having people both from Europe and the U.S. on it and so forth. So that's another example of how that the international gestalt, if you will, that was developed on this, in spite of the stresses, ended up coming up with an amicable solution.
The interesting aspects about this story is, despite all of these sort of conflicts involved, things do happen. Things did happen. And seemingly, in the early 80s, ESA kind of really saw the cancellation of the U.S. Spacecraft as, to them, it was a big deal. It was a kind of a breach of an agreement, almost as if they would breach any other political treaty. But despite all of that, things do still happen.
Yes.
Okay. Mr. Burke, I would appreciate your insight as to the role or the effect that the Apollo program had on Ranger. You've already indicated the reduction to just the TV as the payload, but I would be very interested to know if there were other reasons for that related to Apollo especially.
The Apollo program had some effect on Ranger, primarily an indirect effect of causing the community interested in Ranger, us at JPL and the scientists, everybody involved, really wanted some success. And that's why the block of 4 Rangers, 6, 7, 8, and 9, had the much simplified objective of not trying to land on the moon, stop and have a seismometer there, but just go on and crash with the television on the way in. Simplifying the objective, just changing the payload, leaving the bus the same, you see, simplifying the objective by putting the RCA camera payload on instead of the more complicated objective of a retro rocket, a radar trigger, a ball that has to survive, etc. All the things that Soviets did with Luna 9, eventually in 1966, simplifying the objective in the attempt to get a success was the number 1 priority. The number 2 priority was to get some images that might be useful for Apollo. But images can't really tell you what you really want to know. Is the thing going to sink in or upset or whatever? So Ranger did move its objectives towards support of Apollo, but it couldn't really go very far. Taking pictures on the way in is all you can do. And yes, we got 3 beautiful successes with thousands and thousands of good images. Whether the Apollo designers paid any attention to those, I don't know.
Okay, thank you.
So, in listening to all the talks, what strikes me is that perhaps things in the past aren't as different as they are today. It sounds like that in each case there were technical issues going on that were running into political issues and political cycles that were running on time scales that were much shorter than the technical ones. And so I guess I'm just wondering, I mean, right now we're looking with the planetary budget here in the U.S. has already precipitated new issues with cooperation with ESA, not terribly unlike what happened with Ulysses, and we've got we've either got a going out of business sale or we've got a bump in the road, depending upon how things come out, sort of like what had happened with perhaps with the Discovery program. And I'm just wondering, hopefully history is good because it helps to inform the future. And I'm just wondering if perhaps all of you might comment a little bit on, what are the real lessons that we perhaps should have learned from all of this, and how can those perhaps help to inform us of what perhaps we should be doing to keep going forward with all the physical issues today?
You know, it's historians, I guess we never really want to talk about predicting or influencing the future. We're mostly interested in explaining the past. But clearly, we've, you know, seen in multiple papers throughout this conference that the issue of budgetary cycles of political changes means that you have to very much put the current crisis in perspective and realize that your problems aren't new at all. In most cases, there's simply really almost nothing new. It's more of a cyclical nature. That's not a very good answer to your to your question, because lessons learned, probably it's useful for the actors and the participants to just be conscious of this larger context in which they operate.
Follow that in a little bit different direction, but I think it's related. The difficulty on Ranger that caused me to be replaced by Bud Schermeyer, my good friend, originated really not with the 5 consecutive failures over which I presided, but rather with the attempt by members of the scientific community to add space physics experiments, 8 of them, on board Rangers at a time when we were in big trouble already. And my version of it is, look, we're trying to do something about the moon. Space physics is wonderful. Go do some experiments on a spacecraft that's more appropriately suited to that, one that stays out there and goes around and does things. And of course, nowadays, there are hundreds of them doing beautiful space physics in the magnetosphere and all the way out to the Voyagers to the edge of the heliosphere. So space physics is being richly served now, but adding them to the Rangers at the time when we were already in terrific trouble was something I just didn't want to do. And remember, I still thought the project manager had a lot more authority than I really did have, so I pushed back at NASA very hard. That might have been a strong contributor to the capsize of the project and the replacement of the project manager. Argument between those communities. Interestingly enough, in Mr. Neufeld's paper, that exact same dispute erupted again during the discussion of NEAR and the other missions between the space physics community and the planetary geology, et cetera.
At that stage, it wasn't so much a contest or anymore. It was more about differing communities operating in differing worlds and not actually communicating. I mean, you know, Kermija says, I was amazed that the planetary scientists didn't know anything about Explorer, as you know, a famous name in the history of Earth satellite development.
John, yeah, I hate to interrupt, but we have 2 more questions that if we can get them in very quickly with a quick response.
Well, I'm following up on Ralph's question, which you commented that, you know, that we've been through these ebbs and flows before and there's nothing new under the sun in a sense. However, when I've talked with some of the folks from the early days when things really looked dire, and this was back in the early 80s, and I mean people like Lou Friedman, I don't know if Lou's still here right now, I've said, well, how do things compare today on the risks of the planetary program future compared with that? And he said he thinks that it's much worse, that it's a much more dire situation potentially. So as a historian, can you help us mine from the lessons of the past? What are maybe some of the key things that we ought to be doing today in order to make sure that we don't suffer the fate that we could be suffering?
Asked me to help you do the future, and I don't feel at all
But I'm asking you to look into
as
the
an
past to see
historian.
what things worked in the past and just share those. What were the things that really helped turn things around in
I
the
mean,
past?
actually, John Logston would be the better person to talk about the survival crisis of the early 80s than I would. But, you know, clearly having a program of missions, Discovery is a good model in many ways for having a line and a program, a consistent direction, it's harder to sustain something like that with the huge flagship programs. You can only afford a multi-billion-dollar program every once in a while, so it's much harder to keep a sustained project like that. Obviously, there has to be considerable attention to convincing the political establishment that there's still important new information to come out of this, but often it boils down to, as in the case of Tom Kremegis, I'm sure that Barbara Mikulski believed the science coming out of APL and Goddard and Space Telescope Science Institute, the Maryland institutions, were great, but her first concern was, high-paying jobs in Maryland, keep them there. And so obviously, often this boils down to going back to politicians and arguing for sustaining institutions that are contributing a lot to the economy, and science is a nice byproduct of that fact.
Okay, well, I'm going to commit one of the things the sin that I don't condone, which is I'm going to comment more than question. But, I'm going to dispute what Greg said and also somewhat the premise of Ralph McNutt there. And I think there is a fundamental difference today than the past. There's a number of sayings about, those who fail to learn from history are condemned to repeat it. And then there's the saying that, history doesn't repeat itself, but it rhymes. But I think there is a certain, we have learned things. There are things that are different today than back in the period that a number of these people were talking about. We have a decadal survey now. We did not have that process, and I'm a big believer in that process. Having seen it work, I think it has credibility. I think it has external credibility to important political constituencies. And then we have program lines like Discovery, like New Frontiers. I think that one of the big differences, another big difference that we have is you are less likely to see today the big gaps in exploration programs that we saw in the past. I mean, how long did we go between Mars missions? How long did we go between lunar missions? And now those things are much more included in Discovery, they're included in other program lines, and it seems like, I know you guys rely on your day-to-day existence upon, new programs coming along, but I think that there's, I do see a certain progressive trend in, what has happened, that we've learned from some of these errors, and doesn't mean we're not going to commit the mistake again. But
thank you very much. Please join me in thanking the panel.
My last line is that perhaps our troubles were a necessary step in the evolution toward the harmony that we have today.
And that sounds like a good way to go take a break. All right. Thank you also very much to Joan for running a well-timed panel, because we're on time as we go into our break. Remember, we'll be back here at 3:15 for our last panel, which will be a great one too, I'm sure.
Thank you, Joan.